stream is on. I don't know. Well, yeah. Ask Biksha. Yeah. Yeah. No, seriously, I think he's probably trying to staff it.
Yeah.
So yeah, hit him up. Back to the mothership.
Yeah. Well, I won't be a student. So.
Yeah.
So I don't know.
How that? Yeah. Yeah.
Ben's not a student,
No, he is.
He is.
Well, he's like a. I don't know if you have to be a student. I mean, I know he's done classes. He will be in the master's program. Well, I guess we're live right now, so I shouldn't talk about Ben. But yeah, there's that. All right. Are we good? Oh, it says it's off. Okay, wait, let's see. Okay, it should. Oh, wow, it's like cycling on and off. See it now? Oh wow, it's so weird. Cool. Are we up? All right. Great. Good morning, everyone. To everyone on the stream, that's to you because there's only 3 people here. We were at that time in the semester. So for the past couple lectures, the professor has been, keying us in to reinforcement learning. In lecture, we haven't exactly gotten there yet. We've been working on methods for solving MDPs, exact methods. So today we're going to do a quick recap of that. And then we're going to dive into reinforcement learning quickly. And then we're actually going to move into deep reinforcement learning, where we apply some of the stuff that we've been learning over the semester to this field of research. Okay, so here's a slide from Peter Abil. He's a renowned researcher at UC Berkeley in reinforcement learning, specifically policy gradient methods. But he has this nice slide that sort of gives a field landscape of different methods and their relation to each other. So far, all we've been looking at in lecture are dynamic programming methods, such as policy iteration and value iteration. Today, we're going to recap those and talk about some of their pros and cons. And we're also going to discuss a variant of value iteration called Q-learning, and we're going to see why that's more useful to us in the long run than value iteration. And on the left side of this slide, here is the family of policy gradient methods. And these deal with directly optimizing a parameterized policy instead of estimating values of states and actions. All right. Okay, so where are we right now? So right now in lecture, we've spent a good amount of time discussing Markov processes, Markov reward processes, and then Markov decision processes. So we actually came up in lecture with 2 ways to solve these. And part of what we're given is a full description of the environment, basically what we call a dynamics model, which describes states, actions, transition probabilities between states, and these transition probabilities in a Markov decision process are conditioned on the action that the agent takes in a given state. And so in the first method that we described, policy iteration, this is a 2-step method of exactly solving MDPs. The goal is that, well, what we do is we initialize a policy randomly, and then we also initialize a table of values. So to note, these are also tabular methods, because we call them tabular because the value functions, the value function or the action value function, we compute them per state, and for the action value function per state in action, and we exactly store their value in a table. There's no approximation here. So in the first step, policy evaluation, we take our policy and then we evaluate the value for each state. And basically what this means is at a state, if we continue acting using policy pi, what's our expected return going to the horizon? That can be infinite, that can be finite. In the infinite case, we have a discount factor, which helps us avoid infinite sums of rewards. And another thing about this is something to think about on the quiz tonight. So if you're watching, this could be helpful. Another way to think about the discount factor is that at each time step, you multiply the reward at that time step with the discount factor, and it's sort of like a probability of the process continuing. So instead of just thinking of it in terms of myopic or long-sighted opinions of the rewards you're getting, that you trust rewards that are closer to the current time than in the future, it's actually just saying like, say gamma's 0.8, 80% of the time. So we have an 80% chance of ourselves keeping playing. So that means all rewards from now we're going to wait 0.8, and then 20% of the time the process ends right now, and then we throw that possibility away. So that's another way to think about it. Once we evaluate this policy, we can then update it. We can then update our value function, and it's proven that if we keep doing this, we'll keep changing our policy, and because there's a finite number of policies, eventually, well, we're going to keep changing it, and it will improve. We have monotonic improvement. Therefore, in the worst case, we'll have to go through exponential number of policies, but we are guaranteed to arrive at an optimal policy. So there could be a set of these, not just one. All right, but what if we just said, why can't we just go ahead, estimate the optimal value function, and then from there, the optimal policy just drops right out? Well, we can, but let's chat a little bit about, the trade-offs of these. All right, so what we just said, policy iteration, 2 steps, evaluate, then that should be update, not up. All right, it's computationally cheaper than value iteration, because in value iteration, in each state, you have to go through all possible actions, whereas, and I mean cheaper in per iteration computation. You don't have to consider every action, you just use the policy. And what tends to happen is the policy can converge before the values do. So this can end up just being faster, right? So you can settle on a policy even if your values aren't exactly there. In value iteration, on the other hand, you can have a simpler implementation because we're just, it's not a 2-step algorithm. But at the end of the day, we're not really going to care too much about that. Now we need to consider every so this increases the complexity of our computation at each update, and we have to go until we convert our value function converges, which we didn't have to do in policy iteration. So not necessarily is great, but in general, the value function will converge faster than it would in policy iteration. So there is a trade-off. So it's not like one's obviously better than the other. All right, so at some point, we're going to have to just give up on the model. We don't fully understand, in most problems, we don't fully understand how our world works, nor do we want to understand all the dynamics in general. Obviously, these models are very powerful because we can solve them exactly. And if we're very, very confident that they're accurate, then this is great. But if we make one small wrong assumption about some transition probability, this error can propagate through the model, basically rendering all of what we tried to do useless. Also, just in terms of feasibility in the real world, as the state space and action space grow, having a dynamics model such as like, a transition probability table becomes infeasible too in terms of space. All right, so something that we naturally want to do is we want to learn by trial and error. We want to have an agent that that naturally has access to the environment, meaning it's just someone who can act in it, and we want them to be able to act based on their current knowledge, their prior knowledge of the environment, receive some observations, rewards, and then update their knowledge to better accumulate reward. So basically, the idea is this: without access to these dynamics, we can only sample transitions and returns. So we can it turns out that we can actually use some of these methods to do well in the sample average. And there's some proofs later on, which I'm not going to get into too much detail about, but specifically for Q-learning, we can exactly solve these MVPs by visiting all states in action pairs infinitely often. So that's kind of an interesting thing to think about visiting something infinitely often. All right, so can we adapt policy and value iteration to this sample world where we don't have access to any dynamics and we're just merely experiencing what they call trajectories, meaning just bunches of episodes in the environment itself? So in value iteration, does anyone think that they could think of some way to estimate this quantity using samples? So basically, the problem that we have here is this max over actions. It's not exactly clear how we're going to, after taking a bunch of samples, how we're going to get an estimate of the max action. That's not exactly clear. So how about policy evaluation? Well, this looks a little bit more promising because of this expectation. And it's an expectation over transitions under a policy. So it seems like if we follow a policy and we experience a bunch of these transitions, it looks like that, as the number of our samples increases, we can get better and better at estimating this. So policy evaluation seems promising. What about policy improvement? Well, it looks like we have the same problem that we did with value iteration. All right, so we got to scratch those two off. So that kind of sucks because it looks like we can evaluate a policy using samples, but it doesn't look like we can really do any improvement. Or so we can randomly initialize something and figure out how good it is, but we can't actually improve and do better. All right, so this is where Q-learning comes into play. So it turns out that Q-learning is based on the expectation of the transitions too, estimating the action value function. So you can see this first line is the expectation given the dynamics model, the PS prime SA. The next line, we can just rewrite it as the expectation over transitions. And so we'll just replace the expectation by samples. And by samples, that just means running our agent through the environment a bunch of times. And we're just now, because we don't have as we run through, we don't have a clear, like at each step, we're not actually getting a true estimate. So we're going to have a running average of Q for each state action pair at every time step. And again, this is a tabular method, so we have an explicit value of Q for every state action pair. And this is the update rule. One thing to think about here is that like, for the expectation to work out in sampling, just, basic statistics, we need to basically go over all possible transitions, and we need to do that multiple times for it to really work out. So this brings us to exploration. So back in the MDP solving days, when we were estimating the value of a state, we had to integrate over all actions. We don't have that luxury, we can't do that now. We can integrate over them, not really integrate over them. We can get the sample average by seeing these things multiple times. So basically, how should we act in order to achieve an effective sample estimate? So one idea is maybe we act greedily. Maybe we initialize Q randomly, and then at each state action pair, we say, well, what's the best Q? And then we act, and then we just keep going like that, and we keep updating our Q estimates based on the algorithm provided earlier. Does anyone see the problem with that?
We'll just keep visiting the same places over and over again.
Yeah, exactly. It's just like you have a naive perspective on the world, randomly believe some actions are better than others, and you'll be, because of that max, you're going to keep reinforcing the fact that those are the best values, and you're not going to explore at all, and you're going to miss a lot of your state action space, and we're not going to get anywhere with that. So one idea is this, just very simple, like have some variable epsilon or some hyperparameter, and then we act greedy 1 minus epsilon amount of the time. So you can imagine epsilon being a tenth. 90% of the time, we're going to act according to Q. But 10% of the time, we're going to explore. We're going to sample a random action in the state that we're in. And because of some guarantees that we get from Q learning, which I'm going to discuss later on, we tend to anneal epsilon during training as the estimates become more reliable. But there is a more formal reason for that. All right, so now I'm going to actually swap it up a little bit. We're going to move to something that's a little bit less reinforcement learning, but it's going to sort of illustrate the exploration trade-offs. All right, so I have a little notebook here that you guys can download in the tutorials. So I say Recitation 12. This is a typo. We're actually Recitation 13. So under Recitation 13 in the tutorials. So the n-arm bandit problem is like a super classic problem. So imagine you're in Vegas, and you have n slot machines, which they used to call bandits. Maybe they still call them bandits. I don't know. I haven't been to Vegas.
They don't even have the arms that you pull down on.
They don't have arms anymore?
Buttons, you push buttons.
Well, that's just sad. Well, today we're going retro. We have the big metal arms, and in this case, this is the 10-arm bandit. So there are 10 slot machines. And you start out with some prior belief. Each slot machine has a distribution with a mean and a variance. Each one is so they're independent of each other. And the idea is that you're gonna pull the lever, and you're gonna get a reward from this normal distribution, given underlying parameters that you do not know. So the idea is that what this turns out to be like is a one-state MDP. So your action is select a lever, and as you play the game, the goal is to accrue reward. Interestingly, as you play, you start to learn which machines have better statistics for you. Higher mean reward. But the question comes down to, if you pull a lever and you get a whole bunch of reward, do you keep staying pulling? Given that you have a limited number of pulls, do you keep on pulling that same slot machine, or do you decide to change it up and explore? So here in this example, we have different values of epsilon, of greediness, and sorry?
What is K means?
K and self.k?
Yeah. Q is a Q function, right?
Yeah. Q's the Q function. What is K here? I wrote this a while back.
Is a function of state and action.
It's the value. Yeah.
So it's two dimensions.
Sorry.
The equality is two dimensions. One dimension is state and another is action.
No, there's one state. So your Q function is just the size of your number of actions, right? Because the idea is that like as you pull the slot machine, that's an action. So like I'm in the state right now. I'm in the casino. Every action I do doesn't change anything. I pull the slot machine. The slot machine still has the same statistics. The machine doesn't change at all.
Your state doesn't change, basically.
Your state doesn't change. It's basically one state update here.
Oh, so there's just a one state.
Yeah.
That's why you just have one dimension for
Exactly.
that problem.
Yeah. Yeah.
So if we change another problem which have multiple states, you need to add the state dimension to the problem, right?
Yeah.
Okay.
Yeah. It's basically this example. So this green plot here, you can see the one with epsilon 0, 1, which is the one in between, so 0.1 here. So the largest amount of exploration.
Oh, what is epsilon?
The amount of exploration.
Oh,
It's
yeah,
0.1%.
So 10% of the time you're randomly selecting a bandit. All right, so,
Blue is 1% of the time.
and then red is we don't explore at all. So,
go up a little bit.
sure.
So K maybe means how many samples for this.
Yeah, exactly. Yeah. All right. So it seems like we need to explore, but why? Let's look a little bit more formal. Well, we know why, but I haven't really given you guys anything that's too formal yet. Okay. So one interesting thing. What time is it? Okay. One interesting thing about epsilon greedy exploration is this makes Q learning an off policy function. An off policy learning method. What this means is that we act implicitly in another policy, one that is random epsilon % of the time and follows Q 1 minus epsilon of the time. But we're learning a different policy. We're learning Q. Well, we're learning arg max of Q. That's the policy that we're actually going to learn. Once we're done estimating Q, we're going to go out in the world to evaluate our new policy, and our new policy is arg max of Q. So what this lets us do, so like even if as we train in this suboptimal policy, it's suboptimal because we're acting randomly, a decent amount of the time, the actual Q that we're learning will converge to the optimal policy, which is very interesting. It's pretty cool. But there are some technical requirements. I don't know why LaTeX made it inf. It should be in just infinity sign, but I think that makes sense. But I'm not going to prove these to you, but you can look in the paper from Michael Jordan. If you see Michael Jordan's name in a paper, you should probably go read it. He has too many papers, so you really can't read them all, and they're also usually really dense. So you can. But, no, he has tons of papers. He's very prolific, but he's very well respected. So you can see that what alpha is here. I haven't really discussed this so much. Alpha is your decay. I can go back to the Q algorithm that we put up up earlier. Alpha is the learning rate. So alpha is how much of our target that we assign to the current Q value, right? So of our new estimate, how much are we like so if you set alpha say to 1, that means that at every single step you're saying that the current reward plus well, this term here, the current reward, and then the max alpha action of the next state of your current Q value is your new Q estimate. Not necessarily what you want to do here, but you set some alpha here to parameterize your moving average. So we show that in order to converge to the optimal policy, at each time step, the learning rate must satisfy so the sum, it must be an infinite sum, but the squares of these must be finite in the infinite sum. Interesting result. All right, that's pretty cool. It works really well. We now have a method of moving through an environment, getting sample returns, and then we're actually able to converge to the optimal policy. So even if we don't have transition dynamics, that works out. If we're able to explore enough, and that's the hard requirement. These things are all theoreticals. If you can, technically explore each state action pair infinitely often, but that's another thing. Probably a bigger problem to real practical use is the fact that space complexity grows exponentially in the state space times the action space, size of the state space times the size of the action space. So this is Go here. I'm sure all you guys are familiar with AlphaGo. One of the reasons that DeepMind chose AlphaGo as their big deep reinforcement learning task is the fact that it has the largest game tree that we know of. Much larger than chess. I think it's something like 10 to the 34 size of the game tree. I mean, there are lots of things where you can imagine an image. If you have an 84 by 84 image, each of them has 255 values, you can get a much larger state space. But of a state space that we actually know is a valid position, say in Go, there are actually 10 to the 34 valid different Go positions, which is huge, and you can't store that in memory. And then not even memory. Once you start to do these iterative methods and whatnot, you're not going to be able to visit all those states. Okay, so it seems, none of this stuff is new. No one in 2010, when deep neural networks came out, thought for the first time that you could parameterize this stuff, these value functions. So this has been considered for a long time. In the 90s, there's lots of literature with linear models and other smaller neural nets with some success. But the real success came once AlexNet, the convolutional neural network that blew away ImageNet came out, and also just the not just the creation of GPUs, but the invention of general purpose libraries for GPUs that expanded their usage beyond graphical compute. So it seemed like that we could use deep neural networks to approximate these these functions that are otherwise intractable to compute in a tabular setting. Okay, so I like to think of this as a hack, really. I mean, what we're saying is we're going to take these very established algorithms that have some great properties, stochastic gradient descent, and they only hold these properties under certain conditions. Some of them are the fact that we have a stationary data set, meaning that our data examples are not like the statistics are not changing over time as we train. We assume that the data examples are IID. as we update them, or sorry, as we see them in batch updates. And we assume that each of these batches is statistically representative of the overall data set. All right. So basically, they said, well, screw that. We're going to apply this in an online learning task, non-stationary targets, non-IAD data, all this other kind of stuff, and we're going to hope it works. So, but it turns out, it works. But there are lots of other. Most of the other innovations come around, solving the problems that come with applying a supervised algorithm that expects, a stationary data distribution. All right, so here we have deep Q learning, very similar to the algorithm that we saw before. I'm just wondering, did I put the deep Q learning algorithm here? I think I put the regular Q learning algorithm here. Yeah, my bad. Here, I think it's. Well, actually, yeah. Okay, here we go. This is better. Yeah. So here's the deep Q learning algorithm. So this expectation will be our sample estimate, our gradient estimate over samples. But you can see that we have a non-stationary target right now, and also for each sample, each update that we do. It's totally correlated. The next state is obviously dependent on the one before it.
Can I go up later?
Yeah, sure.
To see what's the difference between the normal learning and deep learning. So here is the tragedy for target, right?
Mm-hmm.
I think
Well, here, this is a value in a table here that we're updating.
but here is function
Where here,
parameters.
yeah. So we take the gradient of this, basically what's called the TD loss.
So how you do the sampling?
The sampling? Oh, well,
As expectation.
right. I mean, so here they describe it like this. You basically, for a full episode until it's terminal, you set the target. Or sorry, no, sorry. You don't. So each time you see a transition, you calculate a target. But the reason that it's correlated is because you're going through an episode. Each step, you're taking the reward, the immediate reward, and you're going to use your previous Q estimate. You're going to find the max next action over that for the next state. Which this is actually something called a technique called bootstrapping, and then we then use that as our label that you would use before, right?
So here the label is the label you have before. What that means.
Trying to understand, what are you asking exactly?
So could you explain more clear that what targets S prime here is?
Yeah, I probably should have put a little bit more of the derivation of this.
Why
This comes from the Bellman update.
S prime here, but no S prime in the previous line?
Oh, target of S prime, because it's a function of your because it's a function. So like these are given, right? This S and A are given, but the target is a function of S prime. We have that there because we're doing the expectation
So here,
over next states, over transitions.
here the target is a function, but in the previous line it is not a function, it's a scale.
This This is a function. It is a function.
It's a function of what is the input?
It's a function. Well, okay, sorry. In this, okay, this is why it's kind of weird. We're saying that this is algorithmically, this is what we compute for our update.
So how to calculate from target to target F prime?
It's not it's the idea is that this is this is going to be a sample average over them. So the idea is that we can add these to a buffer.
But the previous line's target is a scale, right? It is not a function.
Yes, I agree.
But in next line, it becomes a function. How it transfer?
What I'm saying is that in the expectation, like we're not just taking this target value and just saying this is this right here. We're saying that this is an expectation over targets.
What do you mean over target?
We do this many, many times, right? We calculate many, many of these
Also,
over many different transitions.
So these are repeated many times.
Yeah. You know, I'm going to get back to you on that. I think this is like a really confusing algorithm overview.
If it repeat many times, you should mark it on the pseudocode.
Yeah.
You use a repeat or loop.
Yeah.
Not,
No, this is from the paper, so I should.
who write the paper?
Vlad Minet, the guy who did the original deep Q learning paper.
Could you write the name?
Yeah, sure. I mean, if you just look up deep Q learning, and just type Vlad, he's the guy.
Okay, I will touch it.
Yeah. Yeah, let me know. I'm sorry this isn't very clear. I'll follow up on this. All right. So, as we saw before, we have a problem with non-stationary data, right? Is that as we are gathering these experiences and making updates, and like as we explore to new areas of the state space, we're not getting a like a representative sample of all the state action pairs, like of all the transitions, right? Like our data is correlated with how well our current policy is doing, our epsilon greedy policy. So what can we do? And as we know, like neural network approximation fails really hard in that case. Like most of our assumptions are based on the fact that our gradients are like in the average are. I will work on phrasing that on that better, but that fails. One way to help with that is to have a replay buffer. So as your agent acts, you keep storing those transitions, because as you saw before in the previous slide, each of these updates is only dependent on the transition. So you agree with that though, that the fact that like you can calculate this gradient over pairs of state, action, next state, reward. So if you store those things, we can sample those at random, and then we can get better gradient estimates, more stationary gradient estimates. The reason that the target is non-stationary here is because every single time, like every update that we're making, we're actually changing this Q value, right? So we can just use an older set of weights, a staler set of weights, in the target. That tends to work better. We can also prioritize high reward experiences. So as you sample your experience buffer, and not necessarily just high reward experiences, but there are other ways to sample other than just total random sampling. Also, it turns out that DQNs are over-optimistic. I mean, it makes sense. So using the max operator, we're making the assumption as we act. Like even though epsilon greedy helps us explore more, we're still we're still getting an overestimate of how good our Q values are. So there's some other frameworks that address this, such as double DQN. And you can pull up those. Here's a little paper here that I linked. Whoa, I didn't want to go there. They actually like fully explore why they're over optimistic. They do that more rigorously. Okay. Let's get back to where we were. All right. All right. I just put this thing up here because this is my favorite football team. And usually, so Sergey Levine is another Berkeley professor who is known for his work in robotics, applying deep reinforcement learning to robotics. And he always uses an example with baseball, but I feel like that's like too American-centric. So I'm picking a much more universal sport, and also the team I like. But they're really bad right now, so I can't really say anything. Anyway, so if you look at this image, and I'm sure many of you have kicked a football in the past, and you would think about it, like how many of you look at the ball, go to the whiteboard, draw out the velocity of the defender and the ball itself, and spend maybe 40 minutes calculating all the trajectories and accelerations and positions and times, and then once you've done all that, then you go back to the field, and then you follow the model that you've built. That just doesn't happen. That's just not how our brains work. And currently the state of robotics is that these massive modular pipelines, and in these pipelines you'll have a vision system that will speak to some planning system that will ultimately speak to some controller, which will then control the voltage on the motors of the robot. And one of the big problems with this is that if you have even the smallest error or assumptions in your vision system, those errors are going to compound all the way down the pipeline. And Sergey, even though we've seen a lot of problems with deep reinforcement learning, with deep Q networks, which turn out to be very brittle a lot of the time, don't apply, don't work on some tasks at all, take millions of samples, they're super sample inefficient. Sergey makes a very strong argument that he's actually shown empirically in some tasks that there are some robotics tasks that are entirely impossible if you do not do them end to end. The compounding of error through your pipeline is just too great. And if you're able to hook up your vision system right down to the voltage on your motors and train it end to end, it's actually easier to succeed in many ways. Not always, but it's pretty hopeful that this is a better direction, and that we're not just going insane, applying these methods that take hundreds of millions of samples and hundreds of GPUs and weeks to learn.
So you have multiple inputs into your controller then, instead of like one input to another input that then goes to another input then to the controller? So it's like
the idea is that your whole system is differentiable, right? So like maybe not down to the voltages, but at least down to the actions that you're going to tell the controller to do. But you don't have an explicit planner. You'll have a convolutional network, some kind of recurrent network. They have some pretty complex end-to-end pipelines that I can share after that they work with in his lab. But you'll see there's a really interesting example where he has a robot trying to place a block in a hole, basically in a slot, and it seems pretty simple. And it turns out if you do it in a classic modular pipeline, actually, sorry, not even classical. All he did is he took his end-to-end system and he cut it in half, and he basically trained to here, took those inputs, and then put them in the next part of the pipeline, or like trained for like learning the position of the arm from the vision, and then took the position of the arm and then fed that into another network that planned that helped to put the block in the slot. That failed 98% of the time. As soon as you fixed that, the robot could perfectly succeed. The error just didn't propagate, and it could adjust itself optimize directly for the task at hand. And that's sort of what we're going to talk about now. So before, we're sort of learning these like esoteric functions, the Q function, the value of following our current policy from now on. But what if we just said, you know what, we have these powerful function approximators. Isn't the policy itself a function? What if we just search in policy space? And many times this can be more effective for a given task, and sometimes, often can have less sample complexity. I say it has less sample complexity in learning, theoretically, because you shouldn't have to explore as much. You're only learning the policy to act. You're not trying to learn some value across many different states that probably don't matter as much. But there are many drawbacks and problems with applying deep neural networks to this, and those cause it to be pretty sample inefficient at the end of the day. So as we saw before, the state value function doesn't prescribe actions. And do you guys see like if you only had the value function, why you would need a dynamics model, right? So like the thing with having the Q function is that it prescribes actions, like max QA, like max action over QA, QSA tells us the best action that we could take given our estimate of Q. But with V, you would need to know the transition probabilities of going to the next state. That way you can use the values of the next state to tell you how good a certain action is. So that's why we estimate Q.
So I'm sure you mean that we need a lot of samples to train the Q, right?
Yeah, in general, right? Because even in the tabular setting, we showed that like statistically, you need to visit each state action pair a lot to get a good estimate. Now imagine that, but with a neural network that is making many times bad gradient updates because it has a bad, noisy, non-stationary gradients. So you can imagine how that snowballs very quickly.
So that means if you want to learn to kick a football,
Mm-hmm.
you need a lot of samples to train that.
Exactly, yeah. And that becomes even, and it also depends on the task, right? Is the task to kick a football given your view, meaning that you have to learn, pose and whatnot, or you'd hope it would have to learn some kind of pose, or are you giving it the joints and the positions and all that kind of stuff in a much lower state space? Another problem with Q learning, that's just a different problem, is that in high action spaces, learning Q becomes pretty much intractable because what you're doing, you're enumerating, right? Like you're taking the argmax over Q values, and if you have a continuous action space, what does that even mean? So
is that possible to learn a smaller action spaces first and then add it gradually?
There's actually research. I've got a friend who's actually working on that. Ideas of like having some like proto action space that's much smaller, and then from there you can do some kind of like nearest neighbors. I don't know. There are a whole bunch of things you can do, but it doesn't generally work as well. You also remember too, like if you have to explore every possible state action, state in action, now you increase the number of actions a lot. All right.
Some things like for self-driving, like you drive one road during the day, well, you have to drive at night, and when it's raining, and when it's snowing, and it's just the different conditions that you have to go under. It's like it's impossible to feed it all of the examples that you need to learn all the different state action spaces.
Mm-hmm. Mm-hmm. That's the other problem with, that's a non-stationary data distribution, or that's a data distribution you'll have to experience for a long period of time. If you're making updates in one example, it's not regularizing to be able to learn in other examples. It'll latch on to things in the dry environment that maybe are actually useless. And then when it snows out, your policy is crap. All right, so this maybe seems a bit more straightforward than what we were talking about before. Maximize the expected return. Sounds, given a current policy that we parameterize with a neural network, the weights are theta. One weird thing that they do in policy gradient methods, they call actions U. I don't know why. I'm sure there's some reason in the literature. They just diverge. So note when you see U, that really means just A. And then we also opt for a stochastic policy because we can smooth the problem and actually backpropagate on it. Like it's, it is generally difficult to take gradients over discrete distributions. Sorry, I mean, not discrete. Well, I'll remember the word. All right. Oh, okay. That should be, that tau should be like tau I, or just, sorry, this tau here. So basically, we consider tau a trajectory. All a trajectory is a bunch of state action pairs up through a horizon. So you have an episode. You gather trajectories in a state taking action in the next state. So just as a way to simplify notation, this is how we're going to consider the reward over a trajectory. Naturally, it's just the sum of the rewards for each state action pair. Note that this is undiscounted here. So that's something a little bit different too. Okay. Ultimately, what we want to do is just optimize. We want to optimize the expected reward, expected return, accrued by an agent acting under a policy, parameterized by theta. This deep neural network. We're just going to call this the utility of the agent. So under the expectation, you can see that like if we have a dynamics model here, we can exactly solve this expectation. So we call just P tau theta is the the probability of following that trajectory under theta, under the policy. So if we have a sequence of state action pairs, what was the probability that actually happened given our environment dynamics? All right, so now we're going to try to calculate the gradient here, because that's what we want to do. We want to optimize our policy directly here. So we just move the gradient inside the sum. We can do that. But we're going to do something a little bit different here, because you're going to see later why we want to do this. So you can multiply by 1. Then we can shift one of the terms under the denominator there. Okay, this first equation is what we had in the previous slide. All right, this is a cool little trick. Recall that the derivative log of a function is 1 over the function times the derivative of the function. So we can kind of do this in reverse. So you can notice that the gradient of the transition probabilities over the function, which is the transition probabilities, well, this is just equal to the gradient of the log of the transition probabilities, or the probability. Sorry, I shouldn't say the probability of that trajectory is the more formal way to say that. Okay, so that's pretty clean. So we can try to estimate this thing empirically. So we're not going to be able to sum over all possible trajectories, right? That's not possible given the number of states and action pairs that we possibly have. So instead, we're just going to do the M rollouts. What rollouts are just you go through a trajectory until the episode ends, or at some point that you choose that you're done. We do the M times, and then we get a gradient estimate. So this is known as the likelihood gradient, ratio gradient. So we're not actually going to be changing the trajectories themselves, but we're going to be increasing the probability of taking that trajectory. So if our agent follows a certain trajectory, we're going to increase the if the larger this reward term is over the sampled trajectory, the greater, the more we want to increase the probability of our policy following that trajectory again, and vice versa, because the policy must normalize, so increasing the probability of one decreases of others. All right, this is a great result, but we still have a problem here because we still need a dynamics model, because we still need the probability of a certain taking a certain trajectory. And we know we can't do that. We've seen that before. All right. Now, I'm asking a little bit heavier here. All right, but it's not actually too bad. So what we're doing here is we're just purely looking at this term, this delta log of the probability of taking probability of tau I. That's just this term here. We're just pulling it out, and we're going to evaluate it further. So you can see that all this is the log of the big product of each transition probability, right? So state, action, next state, and then the probability of us actually taking that action in the given state. So that's pretty straightforward. We just pull the log in here, give the sum. We can push the sum across here. And one thing that's pretty awesome here is you note that this transition probability term here, this sum, is not dependent on theta. So that just goes away. So really cleanly, what we end up with here is just the gradient of the sum of the log of the policy value at each state through our trajectory. So we still call it the probability of the trajectory, but instead we just replace it with this term. So you can see that we only need access to our policy and to our sample, our returns sampled from each trajectory. Okay, so there are some problems with this. The estimated gradient is unbiased, right? So the expectation is equal to the true value, which is good. But it's very noisy. It's high variance. One of the things that you can kind of see intuitively here that would sort of strike you as odd is that for a given trajectory, or for a given under a given policy, we're going to update it based on the cumulative the total reward over that trajectory. So it seems kind of weird, like we're assigning this big bulk of rewards over possibly a long period of time to the policy. We're not really doing good credit assignment of these rewards. So intuitively, you could be following a lot of different actions that don't really have to do with how well you did, and be making updates to them. So you can basically, it'll end up being high variance because you have different policies that are really doing the same thing, but you're still going to update them. All right. One thing we can say is, and then also like as you go through over time, you start doing better and better and better. But that doesn't mean that the next, so if you reach rewards of 100, the next time that you get rewards 100 to 1, it doesn't necessarily mean that your policy is doing that so much more better. It's really only improving a small amount. So one thing that we can do is, it's pretty simple, just add a baseline. So we can increase the log probability of an action proportional to how much the returns are better than what we had before. So you can imagine if you would want to say, well, 101 minus 100, if those were your, so like if your expected return under the previous policy was 100, and now we get a return of 101, well, we want to say, well, we did one better than before. And that's how we should be updating our policy then. Because we did better in this trajectory, we should increase the probability of of the actions that we took under this policy. Or sorry, in this trajectory. Another thing that helps reduce variance too is just modify the structure to remove terms that don't depend on the current state in action. So here we go. So just baseline B, so subtracted off the rewards that we got on each sample trajectory. And then, here we have a little bit of a problem here. You can see that we just take out, you can see that because we're acting on this time step, like the returns are only going to be dependent on the time steps from now onwards. I think that makes sense. Why should we be giving our current action at this at this step credit for things that have happened before? So remember, like intuitively, our baseline is like a measure of like how well we were doing at a current state in our previous iteration. So it makes sense to say, well, this should just be the expected reward from our current state. Well, this is just the value function under a given policy. So just set the baseline to be the value of v of pi. And now we're saying is like how much better were our current returns from what we thought previously. And then if they were better, then we should set the change the policy to be more like this. So they cutely call it a critic because it's sort of criticizing how well you were doing beforehand. But the actual term is the advantage. This sum term here, right? And just sort of based on the explanation before of how much better we were doing. That is, if it follows from that. Okay, so how do we add in this critic for our baseline? I think I'm missing some bars here in this equation. But yeah, this is just very similar to what we did before in just value estimation, but this is like parameterized. All right, so with that, we arrive at the final vanilla policy gradient algorithm. So this is the basic one. So this addresses some of the most basic problems. So it follows from there. You just collect trajectories, compute the returns, compute the advantage, refit the baseline. So refit the critic, and then update the policy using the gradient that we defined earlier, that we derived. So this high variance problem is huge. It means that gradient updates are not always trustworthy. You can have really bad if you have a bad gradient estimate, which is very likely, and you make the update, your performance can crash a lot. So there are examples where you run a policy gradient algorithm, and you start doing well, and all of a sudden you have a bad update. So this stuff really comes down to the optimization. Popular optimizers RMS prop. because it handles sparse gradients better. I think that, I mean, I should probably give you guys a more rigorous definition, but that's something that people have talked about in papers. You can sort of reason why these are sparse gradients, because the gradient is mostly dependent on the reward signal, but in most reinforcement learning environments, the reward signal is very, very sparse. So you can imagine winning a game. You spend 98% of the time playing the game. You spend 2% of the time winning the game. You only get signal when you win. So that can be tough. And then after, I mean, so from here, there's also a huge problem of the non-stationary data distribution that we saw before. So one of the big algorithms that came out 2 years ago was called A3C, asynchronous actor critic. So the idea is that you had a policy network and a critic network. Critic, being this baseline here, which is just a value approximator, and you would basically have a agent acting in a bunch of parallel processes, and they were updating a centralized set of parameters, and they'd actually be doing it lock-free. So they would be calculating a trajectory, computing the gradient, sending the gradient back to the main network, slapping it on, doing atomic writes, and all the parallel processes will be doing that. And the idea was that way you would have a lower variance gradient estimate, and it would be more stationary because it's from agents that are in different parts of the state, acting in hopefully different parts of the state space under different stages of the parameters. Because as soon as you make an update, you get a fresh set of parameters, or maybe after k updates, then those things get beamed back out. One update, that thing turns out to just be very unreliable to work with. So there's a newer version called A2C, where what they do is they have many agents acting in parallel, and they collect experiences. And sort of like the replay buffer in Q-learning, they send those experiences, they bundle them up and send them back to the main processor. Well, actually, sorry, I should have said the reason that A3C is difficult is because you're doing all of the forward, backward computation on the individual agent threads. It's very hard to utilize the GPU. You can't have 64 processes all making requests. GPUs are not very good at doing that kind of stuff. So in A2C, you still leverage the fact of leverage having multiple agents exploring different parts of the state space and making updates concurrently, but you do all the updates. You do all the forward computation, so you get all the actions on a central processor from the GPU, and then you send those things back out to the individual processes. So it's sort of like a back and forth where each agent says, all right, I need actions now, and then I'm going to send you back rewards, and then you give me more actions, and it just goes back and forth like that. And then there are other algorithms past this to do more. I mean, there's generalized GAE, another way of thinking about the baseline, another baseline optimization to reduce variance. TRPO, Trust Region Policy Optimization. That's a really interesting paper. Another Michael Jordan paper, that's why you should read it. In the paper, he explores a method for monotonic and policy improvement, which is really cool. With this algorithm, there are no guarantees that your policy is going to keep improving. You get a bad update, you have some other problems, it can all fall apart. What's really interesting in this paper, which is like 20 pages of solid math, is that he proves this algorithm, which is based on some pretty old numerical optimization ideas of having a trust region around which you're safe to take a gradient step. I'm saying those in very loose words, but the idea is that the result is that you can get monotonic policy improvement. So that, yeah. Do you guys have any questions? I mean, I can go back to earlier stuff. We can clarify some things. we covered everything that I want to cover. All right, guys. Thank you. Have a nice day.